Hi, in this video, I'd like to demonstrate t-scores and z-scores, their calculation, and the ways in which they are similar. So I've got a short PowerPoint and some data in SPSS. First, we have the normal curve, and this illustration is from the Welkowitz textbook. At page 94, you can see the familiar bell-shaped curve, and we've got the standard deviations in the form of z-scores +1, +2 going to the right, and -1, -2 going to the left. The center is 0 because when we're talking about z-scores, the mean of the distribution is 0 z-scores from itself. Remember that a z-score is a standardized score where individual raw scores have been converted into z-scores using the formula that I'll show in a second. But the data will fit this shape. Here's the formula, and all that you do is you take each individual score, subtract the mean from it using the population mean if you have it. Although SPSS will perform this function, calculating the z-score using the sample mean and sample standard deviation. And if we go back to this previous slide, examining the numbers inside, those numbers are the proportions of the curve that fall between each of the standard deviations or z-scores. And that's an important thing to understand here, is that z-scores are standard deviations. In other words, a person who is at one z-score above the mean is exactly one standard deviation above the mean. That's the standardization process. You're taking each individual score and gauging how far that individual score is in terms of its raw score. You're gauging how far that individual score is from the mean in standard deviation units. Okay, so when we convert to z-scores, it's just the simple process of taking the mean of the distribution, subtracting it from each individual score, and then dividing that number by the standard deviation. You're going to do that for each and every score within the distribution if you want the full set of scores standardized. Oftentimes, we're faced with an issue, at least in stats classes, where we have an individual raw score. We're given the means and standard deviations of the distribution that it came from, and we are asked to calculate the z-score for that individual. And that can be easily done. I'll demonstrate that in a second. Before I get to the calculations, though, to compare z-scores with t-scores, it's important to know that they're doing the same thing. T-scores and z-scores are both standardized transformations of raw scores. The raw scores that you have can easily be transformed into z-scores, and then once you have the z-scores, you transform them into t-scores using the formula that I have on the left. By custom, and this is totally arbitrary, but it's the same wherever you see t-scores used, we set the baseline at 50 and the standard deviation at 10. So when you see the formula here where t equals 10 times z plus 50, all that you're doing is you're saying, I'm going to transform the distribution in such a way that the standard deviation becomes 10 and the baseline will be 50. Of course, if people wanted to, they could do a different type of linear transformation where the standard deviation would be some other number and the baseline would be some other number. But this is considered to be a good method for T-scores when clinical psychologists attempt to communicate with those who haven't taken a stats class about their findings. So you'll often see standardized assessments like the BASC or other assessments, the Behavioral Assessment System for Children, express the values of the assessment in the form of T-scores. And all those T-scores do is take the Z-score and turn it into a different scale. And that scale is easier to communicate to people because it's easy to say, oh, your child has a T-score of 60, which is in the at-risk range. It's at the lower end of the at-risk range because they're higher on that value, for example, anxiety or depression, than most other people. And the most other people here would be located by identifying the area below Z in the probability curve, where you see the 34.13. That's the region, the proportion of the population that falls between 0 and 1 standard deviations. So if a person had a t-score of 60, you'd be able to say that that value, 34.13, plus another 50% for the lower half of the distribution, or in other words, 84.13% of the people who are assessed using this tool fall below your child's score. And when you do the hand scoring, or if you do the computerized scoring of the BASC, each method has a way to determine the t-scores so that you don't have to do these sorts of calculations of calculating the z-score and then transforming it into the t-score. It's all done for you. So when we think about t-scores, it's often the case that clinical psychologists or other types of clinicians, medical doctors, for example, express their assessments in the form of t-scores, but not z-scores, whereas researchers will use z-scores often, but not t-scores, but they're doing the same thing. T-scores and z-scores are essentially the same. They're both standardized linear transformations of the same set of raw scores. So in the typical scenario, for example, in an undergraduate statistics class, you'll have problems like this, where you have to take the given information for a distribution. Let's say the mean is 27. You can see I've got the Greek letters there for mu and sigma. So we're given the information that the mean is 27 and the standard deviation is 3, for example. And then we're given a raw score. And in this case, what I've done is I've calculated it out using a raw score of 29. So with this information, with the individual's raw score and the standard deviation and mean for the population, we can compute the z-score. And the z-score is computed like this. There's the formula for the z-score. It's 29 minus 27. Our individual who has a score of 29 is 2 raw score units above the mean, but the standard deviation is 3. So that person has a z-score of 0.667. And then you can use the z probability table to determine the proportion below. That's not my point here. My point in this illustration is the fact that these two things, z-scores and t-scores, are telling you the same thing. We can take that person's z-score of 0.667, turn it into a t-score by taking the formula 10 times z plus 50. We calculate it out by taking 10 times 0.667 plus 50, and we derive a score of 56.67. Now that sounds a lot different than 0.667, but it is in reality the same thing. And the reason why is because uh, these are linear transformations of the raw scores, and both of these systems, z-score and t-score, are doing the same thing of telling you the position within the curve that the person's score happens to be. And we can see that when we map out the z-scores directly underneath the bell curve, and then the t-scores underneath that. You can see that they line up quite clearly. Of course, I've done that myself in this PowerPoint presentation, but this is, in fact, how it works. And both of those values are located at exactly the same position within the bell curve. The z-score of 0.667, and then the transformed t-score of 56.67 fall at exactly the same position. Now, in practice, what an individual using an assessment tool like the BASC will do is they'll, after they obtain the scores on the assessment, either by having the child or the parent or teacher, or perhaps all three of them, complete their versions of the assessment. The raw scores are converted into t-scores using a system that I'm not at liberty to show publicly because it's copyrighted. But this example that I have on the screen was freely available on the publisher's website. So this is free to show. But it also doesn't reveal all of what the questions are. We don't have any of the questions on the screen. The at-risk region, which is the light shaded region, is comprised of those individuals who have a score between 1 and 2 standard deviations above the mean, where the mean is arbitrarily set at 50. And then the dark shaded region is comprised of those individuals who have scores that are 2 standard deviations above the mean. And uh, the t-scores would be 60 to 69 in 70 or above. Those identify individuals at risk for the thing that you're measuring, such as hyperactivity, aggression, anxiety, depression, etc. Or if their scores are 70 or above, then those individuals would be considered clinically significant. And of course, then you would develop a treatment plan. Bouncing over to SPSS, I have an example from the popular Welkowitz textbook, Introductory Statistics for the Behavioral Sciences. And this example is the dorm hall study at page 19 of that textbook. I've added a variable that I call gender, which I won't be using here, but that's for our purposes in class. And the scores here represent, in this artificial example, or it's fake data, the results of a survey that a student conducted at dorm halls where she was going to be going to college, and she wanted to find out, using a survey, which dorm had the most friendly residents within the dorm. You can see the dorm halls identified by numbers 1, 2, 3, 4, but my focus here is just on the scores themselves. We'll use the score on friendliness for this illustration. Now, what I want to do is I want to compute the z-scores of these raw scores. So this column that I have highlighted shows the raw scores. And in order to get the z-scores, I'm not going to do any of the mathematics on it, although I could, and I'd get the same numbers. I'd have to get the mean and standard deviation for the sample. But if you just go to descriptive statistics and then descriptives, and you can see I already have it over here. Let me reset that. I take the variable of interest, in this case score, that's the dependent variable, carry that over into the variable list, and click the Save Standardized Values as Variables, that is not clicked by default, so you have to go down here and click it right here. And what that's going to do is it's going to create a new variable in your data file automatically, creating the z-score for every individual. We'll click OK. It does give me a little bit of output, but I'm not interested in that. What I want to do is go back over here to the data, and you can see that the z-scores have been created. Now, I'd like to demonstrate for you that the z-scores and the scores are exactly the same thing. And in order to do that, what I'll do is I'll go to Analyze Descriptives Explore, because I want the histogram for each one. And I'll take my two variables, in this case, score and z-score. You can highlight two of them if you hold down the Control key, or you can do them one at a time. Carry them both over. Under plots, I'm going to deselect stem and leaf because I'm not going to use it. And I do want the histogram. So I click histogram, click continue, and then OK. And now we have some output. Of course, these numbers are going to be all different because of the transformation. Although the skew and kurtosis are the same, you can see the mean is different. It goes from 10.1778 to 0.000, which is good because that's what it should be. And the standard deviation now is 1 instead of 4.4882. So that's good. The transformation worked. I wanted z-scores, and the z-scores are linear transformations where the mean becomes 0 and the standard deviation becomes 1. But I haven't proven yet that they're the same distribution. And in order to do that, we'll look at the histogram. Here's the histogram for the raw scores. You can see it's got a nice shape to it, nice and normally distributed set of scores, more or less. And I'll get rid of the box and whisker here because I don't need that. I just want to go down to the z-score histogram, and you can see that it's the exact same shape, but the numbers on the x-axis have changed. Raw score, z-score, they're the same thing. And one more thing, I would like to do the same thing with t-scores. Now, SPSS does not have an automated function for calculating a new variable for t-scores, but we can do that ourselves. I'll go to Analyze Compute Variable, and you can see I've already done it, but I want to do it again. So I'm going to call my target variable t-score. And in order to do this, what we do is we take the z-score carried over, because the formula for t-score is z times 10 plus 50. I'm going to use the asterisk, which is the multiplication function, times 10. And I want to put the parentheses around it in order to make sure that we have the correct order of operations when it computes these new numbers. Outside of the parentheses, I'll press the plus 50 button. I use the plus sign on the keypad over here, and 50. Now we can see that I've got this mathematical numeric expression of, in parentheses, z-score times 10, close parentheses, plus 50, and that'll create a new variable, which will be t-scores. When I go back over to the data, you can see that they look like t-scores in the sense that they seem to be hovering around a mean of 50. Some of them are higher, some of them are lower. And I want to prove to you that the t-scores and the z-scores are exactly the same. And again, the way that I'll do that is I'll go to Analyze Descriptives Explore. And now I'll carry over my newly created t-score variable and run it again. And when I go down here to the Descriptive statistics, we can see that the mean is now 50, which is good. Standard deviation is 10. So the transformation worked exactly as intended. A new set of data has a mean of 50 and a standard deviation of 10, which is what we want from t-scores. Here's the original raw score histogram, and you can see the shape, which is now familiar to us for this set of scores. I'm going to get rid of the box and whisker because I want side-by-side comparisons. And when we look at the z-scores, we can see that the z-scores are identical to the t-scores in the shape. Just the numbers on the x-axis are different. Now, the big question is, will the t-scores also have the same shape? And I'll get rid of the box and whisker, go all the way down to the t-scores. And yes, we can see that the t-scores have exactly the same shape as the z-scores. So in terms of understanding these, I'll go back to the previous slide. It's important to understand that after doing these linear transformations, the data retain the shape of their original distribution in the way that the raw scores appeared. It doesn't do anything to change the relationship of the scores to each other. And if you did a correlation between the raw scores, the z-scores and the t-scores, the correlation for each of those pairs of variables would be 1 because they're exactly the same. They're the same things. All right, I hope you found this video helpful in your understanding of t-scores and z-scores.